Welcome all, it's Russ. And so this video is a little supplementary video that I wanted to use to explain why the strings looked backwards inside your code when you actually looked at them in the Mars simulator. The root cause for this is something called Endianness, which has to do with how integers are arranged inside memory. See, it turns out that there are two completely reasonable ways that you might arrange a multi-byte integer into memory. It really comes down to a simple question. When you have an address that points to an integer, we know that it always points to the first byte in memory. So if there are 4 bytes in memory, then the pointer points to position 0, and then there's 1, 2, and 3 as well. The question is, should element 0 contain the smallest byte or the largest byte in the integer? It turns out that on Intel architectures, this isn't true with all computers. Some computers are big endian. But in Intel architectures, the computer is a little endian processor, which means that the pointer points to the little end of the integer. It points to the least significant bytes. All right, let's see how this works and see how it makes strings look very strange. Over here, I've set up a very simple little program. It has a 4-character string, and it's simply going to do a syscall 4, which of course is print string. The argument to syscall 4 is that you need the actual pointer to the buffer that contains the string. And so we'll run this syscall and we'll see what happens. We'll step through this one thing at a time. We have an add I instruction. I apologize, this is so small. I was able to change the size of the editor, but not of this. So this may be a little hard to read, but we've done the add I instruction. We're now going to do an LA instruction. As we know, LA is a two instruction sequence. And now we're going to do syscall. So watch down here below and see what happens in the output. We printed ASDF. All right. Now, so we know that our code works, right? It works exactly as expected. I declared string in memory, and then I went and I used that string. Now let's figure out where that string actually exists in memory. We did an LA into A0, so if we look at register A0, we will see the address. This is 1000 1000. So we can go over here in our data section and look at that. It's already set to show the data, the right address. Here is the address that we're looking for, 1000 1000. You can look at it and everything else is 0, so yeah, it looks like we're looking at the right place. So we've got 66, 64, 73, 61. So when we look at this up in an ASCII table, we can find the characters. Now, something you have to pay attention to here is that we're using hexadecimal values. We could, of course, turn this off, in which case now this looks like some crazy large number, almost 2 billion or something like that. All right. So we're looking at hex values. So if we're looking at hex values, let's look up hex in the ASCII table. Hex 66 is right here. That's decimal 102. That is the letter F. And so hex 66 is F. And what did we have after that? We had 64, that's D. 73 was S. And up here, 61 is A. So that's exactly what we saw here. 66, 64, 73, 61. So it looks like what we actually had was FDSA. Okay, that's a little weird. All right, oh look, there's this ASCII option. Let's switch it. FDSA. All right, that's very strange. Why is it that the letters are backwards? Does that mean that when we print out something in MIPS, we're actually printing that out in reverse? like we're going backwards through the memory? Well, let's try this out. You'll see that I've made some additional code here. I've loaded the address of that string into T0. Of course, I could have just kept A0, but I'm doing that for a little bit of clarity. I'll set it to syscall 11, which of course is to print individual characters. And now I'm going to do a load byte. Load byte only reads a single byte out of memory. And I'm going to say, I want you to do a load byte at exactly the place where T0 points. Okay, so let's do those instructions in our assembly. Here's the LA again. Here's add I to set syscall 11. Here's a load byte. It puts 61 into A0. Let's double check what that is. It printed A. Now wait a minute. We know that the stuff, or at least we think we know, that the string was backwards in memory, and yet when we loaded exactly the byte where it points, we got A. What in the world is going on here? So we have our conception of how we think memory is working, and we have a label message which points to the first byte of a word. And there's a number of different ways we've thought about this. We thought that this was the string ASDF. That's a totally valid thing we might say. There's another thing we thought. Actually, let's write these next to each other. I want you to be really clear with what I'm about to do. I'm going to write different cells. I'm not saying that they're different places in memory. I'm going to write different interpretations of the same data. All right, so this was our version 2 interpretation. We thought of it as a hex number. And the hex number was 66, 64, 73, 61. All right, and then we tried to interpret it. We said, okay, well, why don't you give me characters instead? And what MIPS printed was character F, character D, character S, character A. And we thought that this was pretty conclusive proof that things were being laid out backwards in memory. But then we did one more test to figure out what was going on. And now we said, you know this label that points to a word? It's not really pointing to a word. It's pointing to a particular byte. Remember, that's how addresses work. It's pointing to a particular byte, which is the first byte of the word. And we said, okay, print this character. It's going to be F, right? No, it wasn't. It printed A. All right, that's very strange. All right, let's do another couple of things. Now, what I did next in the code, you'll notice that if I'm going to do a whole bunch of syscall 11 all in a row, I don't technically have to reset the V register every time. I can just change the A register. So I loaded A0, now with offset 1 from our label. You notice that this T0 is not changed, so we're still talking about the same label, and then we'll do a syscall. All right, let's go back here. 2 more steps, and it printed S. All right, so the second cell in memory was S. And then I did that again for the third cell, and it printed D. And then I did it again for the fourth cell, and it printed F. Well, we've now read the message byte by byte, and that's pretty conclusive proof that the string was actually in order inside memory. Okay, this is really, really weird. All right, let's go back and let's change our constant and see what we see. Let's, instead of the string constant ASDF, let's do ASDF JKLM. We'll assemble that. And now let's look at our memory. Now we have the same constant, 66, 64, 73, 61. And then there's a second one, another 4 letters. Now let's switch this to ASCII. We could, of course, look it up in an ASCII table, but by switching this to ASCII, we're just doing the same thing. Here's what what Mars tells us. The string is encoded as FDSA MLKJ. That's really, really weird. What we're actually seeing here is that the data is in order in terms of words, but every word is backwards. What in the world is going on here? Well, if we were to actually do this out byte by byte, what we would see is we'd see a J, then we'd see a K, then we would see an L, and then we would see an M. And I'll allow you to go do that as an exercise on your own to prove that I'm correct. So what in the world is actually going on? Well, the thing that's happening here is not that strings are backwards, but that we have a funny way of encoding numbers. And this is not actually wrong. I know, you're going to look at this, you're going to say, Russ, this is obviously stupid, and I have a lot of sympathy for you. But there are actually some really compelling reasons that I'll get to at the end why this makes a lot of sense, right? Smart people chose this, but it does have a strange impact. Here's the question. Let's imagine that you're going to write some word. And let's do 1, 2, 3, 4, 5, 6, 7, 8. All right, this is an actual value that we want to encode into memory. The question is, how are we going to write this into 4 bytes in memory? One option that's completely reasonable and would seem really attractive here is to draw it out like that. That's a little bit small, but what I've done is I've written it out left to right, exactly like we would like to read it. 1, 2, 3, 4, 5, 6, 7, 8. All right, I can see that. Now let's imagine, though, that we were thinking about this in terms of accessing the individual bytes. Let's imagine that we were thinking of this as like an array. If I wanted to do this exact same thing in a character array called stuff that was 4 bytes long, how would we get this arrangement? We'd have to say that stuff 0 is 1, 2. Stuff 1 is 3, 4. All right, so far you're still with me. You're like, okay, that all seems pretty reasonable. All right, now let's imagine that you've got this number, you want to convert it into that format. How much do you need to shift this 1, 2 over in order to get that first byte? Well, 1, 2 was the high order bits. So in order to get this, you would be doing a shift right by 24. If you had this number and you shifted it right by 24, then you would get just the 1, 2. This is by 16, this is by 8, this is by 0. Now you realize that you've created something that's a little bit of a monster when you want to write a for loop. Because how do you access element 0? You shift 24. How do you access element 1? You shift by less. How do you access element 2? You shift by even less. You can do it. I mean, nothing wrong with it. But it might make more sense if we did this. What if we said that element 0 in the array would be the least significant byte? It's element 0 anyway. Let's make it the things that you don't have to shift at all. And element 1 can be the things that were shifted by 1 byte. Element 2 can be the things that were shifted by 2 bytes. Element 3 can be the things that were shifted by 3 bytes. This is a totally reasonable thing to do, where you say that element 0 within the array ought to contain bit 0. All right, I can see that. But what does this mean about how it's arranged physically in memory? 12 is not at the top. 12 is now element 3 within the array. We put the least significant bit over here and the most significant bit over here. All right, which is correct? Well, feel free to argue. It doesn't really matter. You can take this arrangement or you can take the other arrangement, and I don't really care which one works or which one you like better. You could do it either way. So we have 2 different arrangements of the memory. One is called Little Endian, and one is called Big Endian. It's called Big Endian if the pointer, remember we had a message pointer that pointed to the first character or to the first byte of something? If you put the littlest bytes of your integer where that thing points, then you say it's a Little Endian architecture. Your pointers point to the little end. But if you put your most significant bytes there, then it is a Big Endian architecture, because your pointers actually point to the big end of your integers. So which one do x86 processors use? Well, it turns out that Intel chose many years ago. They could have chosen either one. It was kind of a coin toss. But they decided to use Little Endian. Now, what does that mean? It means that when you have a pointer to a multi-byte integer, the pointer always points to the least significant byte of that integer. So if you have something that's actually a string, it's not an integer, it's actually a string, your pointer to the string by definition has to point to the first character in the string. So message points to the A. It has to, ASDF. It has to point to A. That's just how these pointers work. But it's pointing to the least significant byte if you thought of it as an integer. What's going on here where we read things backwards is that when you're looking at the array of memory that Mars shows you right here, what's going on here is that Mars doesn't know what's in memory. It doesn't know that things are strings. It doesn't know that things are integers. It just knows that there's memory. Okay, well, how are we going to dump it? Well, the easiest way to dump it is to dump it as a whole bunch of words, 4 bytes at a time. If we're going to read words, let's read integers. And so what Mars does is it goes to address 0. And it says, I want to read a word at address 0. That's fine. You're going to read 4 bytes. You're going to read those 4 bytes and they're going to contain ASDF. Or more pointedly, they're going to contain the ASCII codes 61 and then 73 and then 64 and then 66. 61, 73, 64, 66. Those are the ASCII codes for these characters. Well, that's fine. We just read those 4 bytes. But what did Mars actually ask the processor to do? It said, read a 4-byte integer. And so what does Intel do? Intel interprets those 4 bytes of binary data. And it says that the least significant byte of this 4-byte integer I'm reading has hexadecimal value 61. The next least significant byte has hexadecimal value 73. Then we have 64, then 66. And so what's happening literally, here's what's sitting in memory is 61, 73, 64, 66. And then Mars says, okay, I want to read this into an integer variable. So what does it read? Actually, let's move this text underneath. What does it actually read? It takes the 61 and it becomes the least significant bit, or least significant byte of the integer. This is next, followed by this, followed by this. And this is exactly what we saw. 66, 64, 73, 61. So, which is the right way to go? It was a coin toss. You can make a good argument for saying that we'd like to have things line up in memory the same way that we would write the numbers down. But if you do that, then the cells with the lowest addresses are going to contain the most valuable parts of the integer. That's a big Endian encoding. On the other hand, it might make sense to write some code, especially if you're writing some code. It might make sense to say, I want the thing with the smallest index in the array to be the least valuable part of the integer. In that case, you're going to use a little Endian encoding, which is what Intel chose. And therefore, when Mars reads a 4-byte field out of memory into an integer variable, this is how it looks. You don't believe me? Let's do one more test on Mars. Let's create one more variable. All right, I'm going to create a variable here, which is simply the number 12. Of course, top 3 bytes are 0. So we know that the least significant byte will have the integer, or will have the hexadecimal value 1, 2. The most significant byte will have the hexadecimal, or I'm sorry, the least significant byte will have the hexadecimal value 1, 2. But all of the other bytes will have the value 0. All right, let's test it. Let's print out. What was it? Was test int, I think, right? There you go. We'll put that into A0, and then we'll actually do a load word to read it. Then we'll do a syscall. And now I'm going to leave this for an exercise for you. I'm going to have you run this code. Does it print out the integer exactly what we would expect? We expect it to print out the value 18, because hexadecimal 12 is decimal 18. It should print out the value 18, but how are the 12 and all those 3 zeros going to be arranged in memory? I'll let you find it out. I hope this has been useful to you. I hope it's been interesting. I always struggle to keep Endianness straight in my head, but you can always remember, a big Endian architecture, the pointers will point to the most significant byte of an integer. In a little Endian architecture, the pointers point to the least significant byte of an integer. That's all there is to it. I'll see you later. Bye-bye.